Right, we're going to be looking at the idea of tangents and normals and how the calculus can help us with that sort of issue, finding the equations of tangents and normals. So this first little question, it's an example. I want you to draw a rough sketch of the parabola y equals 2x squared minus 5x minus 3, showing clearly its x and y intercepts. So it's zeros and y intercepts, and this is pretty easy. Done this all last term. And there you've got a little view of it there, and the y-intercept is 0 and -3. Okay, we all know this, and the x-intercepts are there and there. Okay, that's something we can do quite easily. The next part, however, find the equation of the tangent at the left x-intercept. So have a look at that. We know we've got to use the equation. Now this is just a rearranged version of slope equaling rise over run. You see there's the rise and there's the run, and in this one they've just changed that around to make it the rise equals the slope times the run. So there's nothing new, nothing different. It's just been slightly rearranged. Okay, and at x equals minus a half and y equals 0, so that's the point on our tangent. We're looking at the tangent at that point. So our equation must be y take 0 equals m times x plus a half. Okay, we don't know what m is, but of course we do know because we can differentiate the function. If we can find dy by dx, if y equals that, well, we can easily find dy by dx equals 4x take 5. And at x equals minus a half, we get dy by dx equals minus 5. So we can substitute that minus 5 back up here. Or we can, why they've got m equals minus 7, I have no idea. Oh, sorry, I can see what they've done. It's 4 times minus a half take 5. It doesn't equal 5. It's a bit late at night here when I'm doing this. M equals minus 7, so we're going to substitute m equals minus 7 up here. And if you see, that ends up y take 0 equals minus 7 times x plus a half. Expand out and clean up, which is easy stuff for us to do. And there it is, y equals minus 7x minus 3 over 5. So that's finding the equation of the tangent at the left x-intercept. And there was the coordinates of the left x-intercept. We used this equation using dy by dx. Okay, that's pretty simple. Now we're going to have a look at the equation of the normal at the other intercept, 3, 0. So we know that the derivative of the function that we were looking at before was 4x take 5. Substituting x equals 3 gives dy by dx equals 4 times 3 take 5, which equals 7. Now, this is the gradient of the tangent. You know, that's how we define the derivative, is the gradient of the tangent at that point. But we want the equation of the normal. So the normal, we know, is perpendicular to the tangent. We know there is a relationship between the slopes of lines that are perpendicular to each other. Okay, it's the negative reciprocal, so the gradient of the normal must be minus 1 on 7. So that's now sort of the equation of the normal must be y take y1 equals m times x take, x1. So m now is negative a seventh. And rearranging this, cleaning it up a bit, we end up y equals minus the 7th x plus 3 over 7. So, finding the equations of tangents and normals at particular points on a curve really is very, very easy now, because we can easily find the slopes of the tangent. Just that is the derivative at that point, and we can find the equation of the normal just as easily, knowing the relationship between the gradient of the normal and the gradient of the tangent. They're just the negative reciprocals of each other. Okay, negative reciprocals, like so if the slope was 2, the negative reciprocal of that is minus 1 over 2. I think you get the point of where we're coming from there. And, oh, okay, so we can rearrange that, put that in general form, but that's about it. So that's where the normal is there at that point. It's a pretty bad diagram of that actually. I think we'll just leave it there. So there's this one simple application of how to use the derivative, how to find the equations of tangents and normals. Go back over if you need to, and next we'll get back onto stationary points.